All right, let's dive straight into this explainer. We're going to be looking at how some of the absolute most elementary math concepts out there actually serve as well ultimate cheat codes for massive, complex problems. We usually think that to solve high-level mathematical mysteries, we've got to use these highly advanced, incredibly convoluted formulas, right? But what if I told you that the key to unlocking some of the toughest puzzles, programming roadblocks, and even literal Olympiad-level equations is the exact same math you learned when you were 8 years old? No joke. Today, we're totally stripping away the complexity and looking at the sheer, raw power of parity.
So to get us started, we're going to look at a seemingly impossible brain teaser. Really picture this with me. You've got 7 cups sitting on a table in front of you, and they are all facing upright. Now, the rules of this little game are incredibly strict. In a single move, you must choose exactly 4 cups and flip them over. If a cup is upright, boom, it goes upside down. Upside down, it flips back upright. You can do this as many times as you want, and you can pick any 4 cups each time. So the ultimate question is, after a series of these moves, is it actually possible to get all 7 cups perfectly upside down? Take a quick second to mentally visualize it. You flip 4. Now 3 are still upright, 4 are down. You flip 4 again. It starts getting really messy really fast, doesn't it?
Well, here's the secret to this whole puzzle. You absolutely don't need advanced calculus to solve it. All you need are the simple properties of even and odd numbers that you literally learned back in the 3rd grade. Honestly, before you start, drawing frantic diagrams or trying to code a computer simulation to brute force this cup puzzle, you just need a solid grasp of parity. That's just the fundamental nature of even and odd integers. And I promise you, by the time we wrap up this explainer, the solution to this exact puzzle is going to materialize in your mind effortlessly.
Here's a quick look at our roadmap for today. We'll kick things off with puzzles and parity, move into even and odd basics, lay down the rules of parity, apply them to solving complex equations, and finish up with some real-world math applications.
Let's jump right into part 1, puzzles and parity, setting the stage. Which brings us to our second section, even and odd basics, where we are redefining the fundamentals.
Okay, so an even integer is simply any multiple of 2, and that's whether it's positive or negative. In algebra, we just represent this as 2n, where n can be any integer at all. This means 2, 4, and 6 are obviously even, for sure, but so are -2, -4, and -6. Simply put, if you divide a number by 2 and you get a clean integer with absolutely 0 remainder, congratulations, you've got yourself an even number.
Now here is a crucial trap you really need to avoid. 0 is absolutely an even number. It perfectly satisfies our parity rules, and it sits right there between 2 odd numbers. But man, it is such a common stumbling block. People always think, wait, 0 isn't anything. How on earth can it be even? But think about it. Divide 0 by 2, and what do you get? 0. It's a perfect integer without a remainder. Plus, if you just picture a number line, every single even number is flanked by odd numbers. 0 is sandwiched directly between -1 and +1, so it behaves exactly as an even number should.
And of course, that brings us to odd numbers, which are really just the neighbors of even numbers, making up the whole other half of our integer universe. We write this mathematically as 2n plus 1 or 2n minus 1. You know these guys. They're your 1s, 3s, 5s, and similarly your -1s, 3s, and 5s. They are simply the rebellious numbers that completely refuse to be cleanly divided in half.
All right, moving into part 3, the rules of parity, the unbreakable laws. So let's take a look at these operational rules because they're absolutely unbreakable. If you add 2 even numbers together, the result is always even. Makes sense. If you add 2 odd numbers, they effectively complete each other, so that result is actually even too. But if you mix them up, an odd plus an even, your result is permanently odd. Now, multiplication is just as rigid. An odd times an odd stays odd. But pay close attention to this next part because it's a total goldmine fact. An even number multiplied by an even number doesn't just give you an even number, it absolutely guarantees a result that is a multiple of 4.
Then we have the same parity rule. If you add 2 numbers and get an even result, well, subtracting them will also yield an even result. I know, it sounds like a small, almost obvious fact, but it has huge implications. Think about it for a second. If you take any 2 integers, let's just call them a and b. Whether they're both even, both odd, or a mix of the two, whatever parity a plus b happens to have, a minus b is totally guaranteed to have that exact same parity. They are a package deal always.
Let's put this to work in section 4, solving complex equations, parity in action.
By just breaking the algebra down into some basic steps, you can really see how a nasty complex equation completely collapses under the weight of these basic parity rules. Take a look at this one. m squared minus n squared equals 2026. The question is, do integers exist that actually make this true? Well, first, we factor the left side to get m minus n times m plus n. Next, look over at the right side, 2026. That is an even number. Now, because our two factors on the left are the sum and the difference of the exact same two integers, our good old same parity rule dictates they absolutely must either both be odd or both be even. Since they multiply to an even number, 2026, they clearly cannot both be odd, so they have to both be even. But wait a minute. We just learned that an even times an even is always a multiple of 4. So ask yourself, is 2026 a multiple of 4? Nope, it sure isn't. Therefore, without doing any heavy lifting or crazy math, we can definitively prove that no such integers m and n can possibly exist. Boom, case closed.
Now, let's apply this to a real JEE main exam problem. For context, that is one of the absolute toughest engineering entrance exams in the world. They asked candidates to find the number of 7-digit numbers where the sum of the digits is even. If you try to calculate this using some complex permutation formula, you are going to run out of time, for sure. But if you start small, you immediately notice a pattern. Look at all 2-digit numbers. Exactly half have an even digit sum, and the other half have an odd digit sum. Look at 3-digit numbers. It's the exact same 50-50 split. The parity is perfectly balanced. So by just generalizing this pattern up to 7-digit numbers, you suddenly realize exactly half of them are going to have an even sum. You literally just take the total number of 7-digit numbers, chop it in half, and you've got your answer in seconds. It's almost like a magic trick.
We also need to talk about squares. If you square an even number, you are always going to get a multiple of 4. Always. If you square an odd number, you always get a number in the very specific format of 8n plus 1. You can test it right now. 3 squared is 9, right? Which is 8 times 1 plus 1. 5 squared is 25, which is 8 times 3 plus 1. It works every time. But you've got to beware of a massive trap here. Just because a number looks like it fits the 8n plus 1 format, that does not mean it's automatically a perfect square. It's a one-way street of logic, and it is absolutely essential to remember that so you don't get tripped up.
And finally, we arrive at Section 5, Real-World Math Applications, the grand payoff.
Let's take all this theory and apply it to a physical scenario. Imagine a boat moving back and forth across a river. Can you use what we just learned to predict its final location without tracing every single agonizing step? So the boat starts on the left bank. It goes over to the right bank and then back to the left, over and over. It does this exact crossing exactly 2026 times. Do you honestly need to draw 2026 little lines on a piece of paper to figure this out? Absolutely not.
Think about it like this. 1 crossing puts the boat on the right bank. 2 crossings return it to the left. Any odd number of crossings places that boat on the opposite bank from where it started, and any even number of crossings perfectly resets its position right back to the starting bank. Because 2026 is an even integer, we know with absolute 100% certainty it is right back on the left bank. No drawing required.
Okay, I'm going to leave you with one final provocative puzzle to solve in the comments, using the parity rules we just mastered. Think about the physical anatomy of a regular book. When you tear out a single page, it has a front and a back. One side is an odd number, and the other side is an even number. What happens when you add an odd and an even number together? We know this. You get an odd number. So every single physical page torn out yields an odd sum. Now, if a student tears out exactly 11 pages, they are essentially adding together 11 odd numbers. Based on all the unbreakable rules of parity we established today, what happens when you add an odd amount of odd numbers together? And ultimately, could that final total ever possibly be cleanly divided by 4? Take everything you've learned from this explainer today, apply those rules of parity, and let me know down below, is it mathematically possible?